Waves are such an important phenomenon in physics that we can take a variety of approaches when beginning to learn about their properties. Ocean waves can be a tricky way to start. After all, we often just think of breaking waves near the shoreline, which is its own complex area of study. Instead, I'd like to invite you to think of a very simple plane wave, a wave that originated presumably very far from the shore, and which is traveling with a fairly easy to identify speed and wavelength. You can see the peaks of this wave represented as horizontal lines at the top of the screen. The point in the middle between two lines, right in the middle of the gap between two of them, would be a wave trough, where the water is lowest. We can adjust the wavelength by adjusting the slider. As you can see, shorter wavelengths are represented by lines closer together. The plane waves hit a water break at the top of the marina. The point of this water break is to calm the waves in the marina where the boats park, but also to give us an opportunity to study some cool physics. When the water wave is incident on the two gaps in the break, new circular waves result. When a wave passes from one point in space to another, what is actually moving? Well, we can imagine that the water goes up and down. After all, a leaf might stay in pretty much the same place when a wave goes by. The wave is a phenomenon, something different than an ordinary object or thing, almost like a set of instructions. When two waves combine, two sets of instructions conflict, and we have wave interference, which is at the heart of this simulation. By the way, a second simulation called Stadium Wave has more information about wave interference, with perhaps a simpler interface, just people standing in a line waving their arms. Check it out. As the two circular waves broadcast outward from the opening in the water break, we see them interfere. Where two lines cross, where two wave peaks meet, we would expect a lot of upward water motion. Likewise, where two gaps cross, where two wave troughs meet, we would also expect a lot of downward motion. We can see that there are regions where all the crossing lines and crossing gaps cross one another. At these points, we'd expect a lot of upward and downward motion. We call these interference maxima and sometimes interference fringes. We also see there are regions where the lines cross gaps, where the set of instructions from the waves coming from the two gaps are in conflict, one telling the water go up and the other telling the water go down. Here we'd expect fairly calm water. That's a great place to park a boat. Let's set the wavelength to 10 meters and then pause the simulation. A set of guiding angles appears. Notice that on the graph above, it says there is a peak amplitude of motion along a 10-degree angle, measured outward from the center of the water break. Likewise, we see on the water pattern itself that gaps and cross lines all line up at around 10 degrees. This is an interference fringe. Let's choose some point on this fringe. If we count the number of wavelengths from that point to one of the openings, and then the number of wavelengths from that same point to the other opening, what do we find? We see that those counts differ by 1. In fact, the reason you get interference along this fringe is that one wave arrived a full wavelength ahead of the other, and they interfered with each other constructively. We see another fringe at about 18 degrees. If we again counted the wavelengths from any point along that fringe to each of the openings in the water break, we'd find a difference of 2 wavelengths. Again, the waves interfere because if you shift a wave by exactly 1 or 2 or any integer number of wavelengths, you get something that looks very much like the original wave. The counting of waves and wavelengths explains the fringes we see in the wave pattern. This is a defining feature of waves. What happens if we take away one of the openings so there is only one remaining? Let's also lower the wavelength completely and increase the width of the opening. there is still some kind of interference going on. This phenomenon is known as single-slit diffraction. One model for this that works pretty well is to imagine new wave fronts emerging all along the opening. It creates a broader pattern of interference than the small fringes we saw due to the two different openings. When we go back to two slits, we see that the diffraction pattern acts as an envelope of sorts over the fringes. So we are looking at both interference and diffraction in this graph. The most fascinating thing about wave phenomena is that they arise in such a variety of different circumstances. The same types of interference we see here can be seen with light waves, with sound waves, and even with the quantum motions of electrons. We hope you enjoy this simulation.